As a third topic of today, let's solve one example beam bending beam design problem. So in this problem, we have one simple support at the midpoint. It's not exactly midpoint, two-third point of the beam, and we have non-uniformly distributed loading from the top, and the non-uniformly distributed loading can be written as Qx equals to be W0 over L multiplied by X. So when you look at this problem at a first glance, you might wonder if this structure would satisfy static mechanical equilibrium. But when you look at the numbers carefully, you see that it can satisfy the mechanical equilibrium. So to answer this question, like to answer the maximum sigma x point, what you have to do first is you have to first obtain m as a function of x, and out of this distribution you have to obtain maximum m, and out of the maximum m point you have to obtain sigma x distribution to answer this question. So to do so, before applying rule 1, rule 2, rule 3, we have to obtain the reaction first. So this is unknown reaction, and we have to obtain that first. For this problem, interestingly, because this distributed loading is located like 1/3 position from the right ends, what you can see is statically equivalent problem can be designed as like a half of LW0. This is the total force applied for the entire top surface, and statically equivalent problem can be devised by placing this point of force at the center of this weight, and center of this weight is 1/3 position because it has triangular distribution, and this is our statically equivalent problem. From here we can obtain the reaction force as half LW0. So after obtaining this reaction force, we can obtain the free body diagram like this. We have distributed loading, we have this point of force, and based on these two information, we can obtain the force and moment at A point, B point, and C point. At A point, this is the free ends, M must be 0. And of course, this is free ends and there is no sidewall. BA must be 0. At the right end, at C point, we have MC equals to be 0 and BC equals to be 0. Now at B point, we have delta V equals to be half W0L, because when we have the downward force, delta V is minus PE. Here we have upward force. The force discontinuity should be half W0L, and the moment at B point must be 0. So this is how to say our information about A point and B point and C point, the three critical points. After placing the information here and there regarding B, A is 0, B at C equals to be 0, we have to first obtain the B distribution. So to obtain B distribution, we're gonna use Bx equals to be negative Q x dx from 0 to x, because Bx equals 0 is 0. So from this relationship, by plugging in Qx equals to be W0 over L multiplied by x, you can obtain this distribution up to this point. So we have Vx equals to be negative W0 over 2L x squared. Then after identifying this point, we have to use this information. Delta V must be half W0L. If you add up that value, half W0L, you're gonna have 5 over 18 W0L at the just right of this support. Then from here to the end, you have to do integral Vx minus value at this point, and you do integral from 2/3 point to arbitrary x. Okay, then you can obtain the distribution from this support to the end, and the distribution should be something like, because it has positive Qx and the magnitude of Q continuously increases from 0 to L, this slope continuous exponentially increases magnitude of slope. So this is the V distribution. After obtaining V distribution, how we can obtain M distribution? Yeah, what you can do is, we do integral. So from x equals 0 to 2/3 L, from here to there, MA start from 0, and then you do MA, and then you do simply this integral, and the V expression before 2/3 L point is relatively simple, minus W0 over 2L x squared. This is the Vx information. So if you plug this number, and then what you're gonna get is you're gonna get mx equals to be minus W0 over 6L x cubed. Okay, so this is the expression regarding the M up to to third point, and from here to the right end. At the right end, M should be 0, and from this point to there, you have a positive V, which means that slope is positive number, and this should be the distribution of M. Of course, as the M diagram approaches to x equal L point, slope must be approaching to 0 because V approaches to 0. Okay, and the maximum magnitude of M at this support turns out to be minus 4/81 W0 L square by plugging x equals to be 2/3 L. Okay, so with that, we identify that out of the original problem, this is the point with maximum M value, M absolute value. Having identified the maximum M value point and the magnitude of M at that point, so we can now rely and use the flexure formula. And to use the flexure formula, we have to consider the area moment of inertia first. And for the cross section, for example, let's suppose that this problem has this square cross section with width A and height A, and if we obtain the area moment of inertia, it will be simply 1/12 A force power, and the maximum distance from the neutral plane to the top or bottom is A over C. So if you plug in this information, A over C at the position of C, and I equals to be 1/12 A fourth power, then you can obtain the maximum sigma x point by also plugging maximum M value here. Okay, so after massaging the equation, what you're gonna get is 8/27 W0 L square over A cube. Okay, so here what we have to realize and learn is, in addition to simply relating the sigma and M in this problem, we have to also obtain the full information about M over the entire beam, and out of the entire beam position, you have to locate the position with maximum absolute value of M. After that, you apply the knowledge we have learned back in chapter 4. Okay, so this is a problem combining the knowledge in previous chapter and the knowledge in the current chapter. Okay, so with that, let me finish today's lecture.